Welcome back to the final video in complex eigenvectors and stability. This one we do want to look at this idea of stability and phase portraits as well. Okay, so what you can see here is we're going to look at the length of this dynamical system. So how far away it is from its initial value. Okay, so we want to know what happens to this length if r is bigger than 1, r is 1, and if r is less than 1 but bigger than 0. Okay, so first thing is if r is bigger than 1, what you can imagine is going to happen is that you're going to have some starting point. Maybe you have it here. Okay, and x1 and x2, imagine those are your real and imaginary axes. But if r is bigger than 1, you're going to begin to get further and further out from the origin every time. Okay, and we're going to progress counterclockwise because that's normal direction. Oops, that way. Normal in mathematics. Okay, so this would be the picture of r is bigger than 1. That's the behavior that we would see roughly. We're rotating and we're scaling all the time, so we're going to see some sort of circular motion. Okay, if r is equal to 1, as you might imagine, if we begin something like this, what we're going to see is we're going to kind of stay in an orbit around some central point. It could be this point, whatever, but we're going to move like this, and similarly we're going to just kind of stay in some sort of orbit. Okay, and then lastly, if we have something where r is between 1 and 0, exclusive on both, what we're going to see is if we begin away from the origin, it's going to sort of spiral in. Okay, and this time I'm still going counterclockwise. And actually, first one I was going clockwise, so my bad. But we should be going counterclockwise. Okay, and we would spiral and decay towards 0. Okay, so if we consider a dynamical system in general, what we're going to attach to each of these different cases is this idea of stable equilibrium, and that just means that it decays to 0 as we iterate through the system. That's really all it means. Okay, limit 0, blah. Okay, for all vectors. That's another important piece, is that for any given initial value, you're going to decay to 0. Okay, so then the next question is, I have a few examples here. Let me zoom out so you can see each one of them. And the lines you see are meant to be the trajectories or the eigenvalues and eigenvectors. So I'm going to have you pause the video and determine which of the following are stable, if any. And the two in the upper right end up being stable because they, again, decay to 0 over time. The other ones, the upper left and bottom middle, those are expanding and getting away, so those are highly unstable. And then the one in the lower right does a little bit of both, like it decays 0 and doesn't, but you have to, again, have all vectors decaying to 0 for it to be stable. Okay, and then the other one is an orbit, so that doesn't do anything. Okay, so now we want to discuss how to draw these things. So if we have a given dynamical system, blah blah blah, we have complex eigenvalues, and we can talk about r as being the absolute value, which is really the magnitude, if you will, and so we want to find, and the value of r should be the same regardless of eigenvalue if they're complex. Okay, if r is equal to 1, what is going to happen? Well, we're going to say the points of x of t are on an ellipse. Right, that's an orbit. Okay, if r is bigger than 1, the trajectories spiral out. And if r is between 0 and 1 exclusive, the trajectories spiral inward. Okay, and in these cases we would say that the only case where they are stable is this last one, and the other two are unstable. Okay, so to wrap up here, we have one final example. So we have a system here with the initial state vector, blah, blah, blah. Find a closed form for this and sketch the trajectory. So what we have is, if you go ahead and find the eigenvalues, they end up being 1 plus or minus I. Okay, and then if we look at lambda 1, which is 1 plus I, that's going to have eigenvector 2 plus I and 1. So then that makes our matrix S, right? That makes that 1, 0, 2, 1. So, okay, great. And then if we wanted to write this all out, we could write it as x of t is equal to, and then the length of this vector would be root 2, so this r is root 2 to the t, and then we have matrix S, and then we would have matrix of cosine theta t, sine theta t, minus sine theta t, cosine of theta t. I still haven't found what theta is, but we will get there, I promise. S inverse, and then times the initial state vector 0, 1. And then just remember that theta, we can find that as doing tangent inverse of 1 over 1. Okay. So that comes from our eigenvalue, right? We could plot it, and then in polar form it would just be 1, 1, boom, boom. So then our theta would be that angle in there. So we get a whopping pi over 4. Okay, so you could replace all the thetas with pi over 4. I'm lazy. Okay. So here we go. We want to just finish up here. And to do that, if we imagine plotting this on the real and the complex, or the imaginary, rather, if we start at 1, 0, because r is equal to root 2, which is bigger than 1, we have an unstable orbit. So we could do the calculation, and for instance, we could plug in the first iterate and see what happens. Well, we're going to rotate and move out, so we're going to move from here out to like here, right? And then it's going to progress in a spiral outwards. So we're going to see some sort of behavior like this over time. You could continue the calculation to find the exact values, but that's the overall idea. Okay, so main ideas here is for stability, we want to find that r value, which is the square root of p squared plus q squared, coming from the real and imaginary parts of your eigenvalues. And then from there we can talk about stability. Anything that is stable will decay to 0, and anything that is unstable will either remain in a constant orbit or will spiral outwards away from the origin. Okay, so that is the last video for this section, and we'll talk more in class.